Hello everyone, welcome to Chapter 8, Section 6, where we're going to be talking about radical expressions and introducing the idea of rational exponents. So in this example, we're going to mostly discuss a little bit of vocabulary, but do a little bit more with understanding the concept of what a root is. And we've used the word root before when we said like the root of an equation. And that's quite frankly kind of odd or weird, but most of the time you're going to hear it when you say something like square roots. And square roots are a special type of this idea, and we're going to introduce what the other ones are going to be in this section. So just let's think about this for just a little bit, right? So we know that the order of operations, we say PERMDAS. And I know some of you learned it like this, PEMDAS. I'm sorry about that. These two actually go together because, like we learned before, and especially in Chapter 8.3 where we were adding rational expressions and subtracting, subtraction really doesn't exist. It means adding the opposite. It doesn't really exist algebraically, I should say. Same thing happens with multiplying and dividing. So in this case, we would if we were dividing by something, we would actually multiply by the reciprocal. That's the same idea. These are actually, if we do include division, subtraction, that's fine. They're actually inverses of each other. So when I solve and I have an equation like x plus 5 equals 11, the opposite of adding 5 would be to subtract 5. So I work backwards. Those are called inverses, inverse operations. Same thing with multiplying and dividing. If I have an x divided by 3 and that equals 4, then the opposite of dividing by 3 would be multiplied by 3. So then if we ignore this one, we get to the e, which stands for exponents, and we say, well, all these other operations have inverses. What's the inverses here? And that's where we're going to bring in that idea. So we're going to talk about radicals and roots, and that R actually stands for radicals and or roots. You can choose either one. That's what the R is going to come from. So let's talk about exponents for just a moment. We've seen this before. We've used it a lot. We did an entire section in Chapter 5 over x to the second power. For an exponent, just so that we are aware of what's going to happen, if I have, for example, let's say, sorry, the one I was gonna use is like one of the examples I have set up here, so I'm trying to think of another one. If I have like 3 times 3 times 3, we'll say one more, so we're using a different number. You remember exponents. The way that we write this would be 3, and then we count 1, 2, 3, 4, 3 to the 4th power. Okay. So now we're going to reverse that. I know 3 to the 4th power, that's 81. So what I can do is I can find what's called the 4th root of 81, which is this. I'm using the same thing. So this means what number times itself, and one more time. 1, 2, 3, 4. That number right there is called the index of the radical. And then I go, well, what number times itself again is going to equal 81. And like I have here, I've got 3 times 3 times 3 times 3. Now, we've done this a lot of times, like I said, with Chapter 5, where we have, for example, 7 times 7. And we say, okay, we're going to write that like 7 to the 2nd power. So if I reversed it and said, what's the square root of 7, then that's actually asking what number times itself. These two have to be the same. I'm sorry, that's where I'm starting to mess up. This would be, let me rewrite this. Square root of 49. I forgot to do the 7 squared. Sorry. So it'd be like, I would be asking what number times itself equals 49. And like I have here, 7 would be one of the choices. Maybe there's another number, and we'll talk about that. Now notice that I didn't write anything right here. That's because it's implied that it's the second root or the square root if you don't see anything. And we've seen lots of examples of that. I keep reminding everyone that algebra is a language, and how we say and how we write things sometimes gets a little confusing. So keeping up with the idea that you can always show the stuff that's hidden, yes, if you put a 2 there, people are going to look at you funny, but I won't, all right? So if you do not see an index, then that means that the index was originally 2. So these things that get repeatedly multiplied, those are going to be the roots of this number. And if I've got fourth root, then I have 4 of them. And if I've got the square root, then I've got 2 of them. So we say square root if there's 2, because, you know, this is 7 to the second power, so we say 7 squared, so this is square root. We also, for example, if I got 9 times 9 times 9, that's going to be 9 to the third power, so we say 9 cubed. Excuse me. And if I wanted to find the third root of 9 cubed, which is 729 by the way, but if I want to find the third root of 9 cubed, then this is asking, and I'm drawing arrows, I'm not saying it's equal to it, but it's asking what number times what number times what number equals 729. Of course, that'd be 9 times 9 times 9. And please, I want to point out, I'm not setting anything equal. Okay, 7 times 7 does equal 7 to the second power, but the cube root of 9 cubed, that would just lead me to this idea. The cube root of 9 cubed equals 9. Right? Not 9 times 9 times 9. I have to think about how you guys interpret what I'm saying. All right, so there's going to be some examples, and this is all going to be with words. We're going to find the fourth roots of 81. We're going to find the cube roots, that means third roots, of negative 125. You can read the other ones. So what this is asking is what number times itself. These are all the same. I'm not just picking 4 different numbers. Okay? These all have to be the same. What number multiplied by itself again, is going to equal 81? So you can try different things. How you figure it out, it's kind of like a puzzle trying to figure it out. But generally speaking, if you're good with multiplying, you should be okay with this. So it's not going to be exceptionally big. It's not going to be 1 times 1 times 1 times 1, because that equals 1. 2 times 2 times 2 times 2, that's 16. 3 times 3 times 3 times 3. 3 times 3 is 9. 3 times 3 is 9. 9 times 9 equals 81. Or 3 times 3 times 3 is 27, times 3 more is 81. So this is going to be 3. So the fourth root of 81 is 3, because I don't have room here. Because 3 times 3 times 3 times 3 equals 81. However, there's also another one that we have to be mindful of. Excuse me. The other one would be negative 3. And for the same reason, 3 times 3 times 3 times 3 still equals 81, but then we have to check, does the negative work? And the negatives go like this. A negative times a negative is a positive. A positive times a negative would equal a negative. And then the negative times the final negative would get me back to a positive. So if the root that I'm looking for, the fourth root or the square root or the sixth root, if that is odd, 2, 4, 6, 8, 10, then there's going to be 2 of the roots. One's positive, one's negative. And remember that with square roots from chapter 5. We had square roots. So if I said like x to the second power equals 25, then I would take the square root of both sides, I get positive 5 and negative 5. So that's what's going to happen here. It's going to be a little different with cube roots. What I'm asking for here is what number times itself equals negative 125. So again, you can do it by trying different things. We just said that 3 times 3 times 3 equals 27. So it's not going to be that. And also you can kind of reason it out a little bit. I know that if it's 4, before I even try to multiply 4 times 4 times 4 and get 64, I know those are all even numbers, and I ended up with an odd number. If I multiply by an even number, my sum has to be even, because it's got that factor of 2 in it. And actually, the 4s have a lot of factors of 2 in it. All 2s, as a matter of fact. Since it ends in 5, probably it's going to be 5. So I know that 5 times 5 times 5 equals positive 125. Okay, that's negative 125. So what do I have to do? Well, let's think about it. What if I have a negative times a negative? That's a positive. And then a positive times the third number, which is negative, that goes back to negative. So again, if the root that I'm looking for is even, second root, fourth root, 6, 8, 10, etc., then I'm going to get one positive, one negative root. If the root that I'm looking for is odd, the third root, the fifth root, 7th, 9th, 11th root, then you're only going to get one of them. If this was positive 125, my cube root would be positive 5, not negative 5. But in this case, this is going to be negative 5 and not positive 5. Okay, so let's look at this one. I've got the sixth root of negative 729. So what number times itself again, times itself again, and times itself a couple more times? So I got 1, 2, 3, 4, 5, 6. Which number is going to fill in that box? Of course, these all have to be the same. That's going to give me negative 729. All right, so here's what I do know. I know that 3 to the 6th power, 3 times 3 times 3 times 3 times 3 times 3. That's why I use exponents, so I don't have to rewrite that. This does equal positive 729. Because if I look at it, positive, 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 everything's going to be positive. Okay, so that makes me think like this one, maybe what if my root is going to be negative 3? All right. So if all of these are going to be negative 3, I'll put a question mark. Negative 3 times negative 3 is positive 9. These two are going to be positive. Negative 3 times negative 3 is going to be positive 9. Positive times positive is positive. Negative 3 times negative 3 is going to be positive 9. So I end up with positive times positive times positive, or starts negative, then positive, negative, positive, negative, positive. Because that's even, all of the negatives multiply in pairs, and you end up with positive 729. So for this one, there is no 6th root. And we are going to ignore taking the square root of negative numbers, which we talked a lot about in chapter 5. So we're only going to deal with numbers that are on the real number line. All right. It gets a little complicated once you start to get in there, and that goes beyond the purpose of what we need to do here. We're just introducing this idea. Same idea. I have the fourth roots of negative 256. So since I'm looking for 4 numbers that multiply to give negative 256, I can say one more time, there is no real fourth root. I should have wrote the word fourth, but that's okay. Because a negative times a negative would be positive. Positive times negative goes back to negative, and negative times negative goes to positive. So I'm going to end up with a positive number. The key is all of these have to be the same. Okay, we're going to talk more about roots and how we write this, the language algebra, in the next video.